in this case, giving this lecture, I represent something called the Anthropocene Working Group. This is a group, an international group of something called the Subcommission on Stratigraphy, which is a body of the International Commission on Stratigraphy. So, you know, we are working in an international body for an international body, and I'll explain more about that as we go along. So let's see, we need to go to the next one. Right, so the idea of the Anthropocene was promulgated by this bloke here. This is Paul Crutzen, an atmospheric chemist. He's a Nobel Prize winner for coming up with understanding of the chemistry of the ozone hole. And back in the year 2000, he was at a meeting of the Earth System Science community, and they were talking about changes within the Holocene, and he said, suddenly interrupted me. He said, "We're not in the Holocene anymore. There's been so much change. We need to have a name for a new geological epoch that we're now in." And he came up with this formulation, the Anthropocene, and it all spun up from there. So the Anthropocene, the idea is that we humans are now so abundant on the planet that through all of our activities, we have actually become a geological force on the surface of the planet. And through our activities, we are in fact creating a new geological epoch. So we have these geological deposits that are forming now. They include chemical and physical fingerprints distinct from those that you would find in what was the current Holocene epoch. And those fingerprints have a high potential to remain in the geological record to be found in the future. Now, the change that we see became recognizable worldwide as a sort of a really major change starting in 1950. This wasn't the first detectable anthropogenic change because, of course, humans, let's see, Homo sapiens started around in Morocco, I think. The oldest Homo sapiens remains are about 300,000 years old. And Homo sapiens then expanded considerably, but in small amounts, and so they didn't have a huge detectable influence around the world until our population got up into the several billions. But in effect, because there are so many of us, the Earth has experienced what we might call a rupture in its functioning. And we're all well aware that human well-being has grown. You know, we have more people living to 100, but the planet has become warmer and more polluted and less biodiverse. And that's important because the planet operates our life support system. And so, you know, there are concerns that if we do too much damage to it, we'll be actually damaging our own life support system. But let's go to the geology and see what we're talking about. On the left is the present geological scheme for the Quaternary. So you can see there the Pleistocene and the Holocene as epochs. And then what you may or may not be aware of is that in just about a year or so ago, the Holocene itself got divided by the International Commission on Stratigraphy into upper, middle, and lower. These are named the Megahallian, the North Grippian, and the Greenlandian. And there already were different stages in the Pleistocene prior to the Holocene. And these stage boundaries are marked by what we call loosely golden spikes. And what those golden spikes represent, the wording is down at the bottom of the page, are GSSPs. The GSSP is the Global Boundary Stratotype Section and Point. So once you've found what you believe in a vertical section to be your ideal boundary for this stratotype section and point, you hammer in a so-called golden spike. And in the diagram on the right, you can see the way in which the Anthropocene, what it would look like if we added the Anthropocene as a new geological epoch to the geological timescale. And on the far right, you can see that the gray spike there for this stage 8 is labeled mid-20th century. And I'm going to explain to you how that came about. So what we what we see if we go back to what our human influence has been, this diagram goes back, it's looking at agriculture and herding over the past 10,000 years. And it's divided into a number of scales. So at the far left, you see a very condensed scale, which is millennia, running from 10,000 years up towards the present. And then you can see that expanded into the centuries time scale for AD 100 up to 1700. And then you can see it divided into decades for the period 1710 right up to the year 2000. And then you can see it divided into years for the period 2001 to 2015. This was published in a paper by Ellis in 2020. So the colors then on the left-hand side, you can see this sort of bluish middle part and the sort of pale grayish underneath. These are wild woodlands and wild treeless and barren lands. And at the bottom, where you've got sort of white just above the scale bar, this represents ice and uninhabited ice conditions. So added to this, then gradually you'll see if you go to millennia on the left-hand side, you can see pale green colors come in. These are populated woodlands. This is the period when humans were running around on the planet just after civilization started with the development of cities around about 10,000 years ago, right almost at the beginning of the Holocene. So the prime activity of humans up until that time in the late Pleistocene was hunting and gathering. And then what we see is that things began to change, and you can see where the sort of a bright green color comes in. We're getting residences in woodlands or residential woodlands, and then you see whole lots of different kinds of crops developing, rangelands developing. I'm not going to go into all the details, but what you're seeing is a phasing in over the right-hand side of the diagram, a phasing in of the processes of herding and agriculture, taking us up to the present day with our dense urban settlements. So you can see here our growing human influence. Also, you can see in the next slide what the changes have been in the world's land mammals. So we've seen, as well as that change in from pastoral to pastoral and agricultural from hunting. So here we see how that's affected land mammals. So the bottom scale, excuse me, you can see we start on the left 100,000 years ago. And at the time, the wild land mammals, there were represented about 20 million tons of carbon. By the time we get to 10,000 years ago, when the human population was around about 5 million, much of it in Europe and the Middle East, then we had that number diminished to 15 million tons of carbon. The reason for that was that hunters during the Pleistocene, particularly the late Pleistocene, hunted megafauna almost to extinction. In fact, they hunted some megafauna to extinction. The demise of the mammoths is one sort of example. And you can see some of the, in places like Lascaux caves, where there are cave paintings, you can see the sort of depictions of animals running around at that time, big animals that no longer exist or are in much smaller numbers. Then we go up to 1900. By the time we get to 1900, that number of 20 million tons of carbon in wild animals has diminished to 10 million tons. And then if you follow that along to 2015, it's down to 3 million tons. So the only 2% of the mammal biomass in 2015 was wild land mammals. And they have been replaced in a sense by us, humans. So if you look at 1900 and you go up to the top part of the colored bar there, by 1900, we had a global population of 1.7 billion humans, representing 13 million tons of carbon. That's almost as much as there were wild animals 10,000 years ago. And then you go up to the top of the scale bar and the right-hand side at 2015, when our global population was 7.4 billion, and we humans represent 60 million tons of carbon. And what you see going along with our growth in our human population is the blue color in the middle of the 1900 scale, This is our livestock, the mammal biomass, goats, sheep, and cattle in particular. Already by 1900, these have risen to 35 million tons of carbon. And by the time we get to 2015, it's up to 100 million tons of carbon. So an enormous change in the biomass on the planet, enormous change in the balance of humans and wildland mammals, and the enormous rise in our livestock. In fact, what we've seen, as it says down at the bottom under the timescale bar, is an 85% decline in wild terrestrial mammal biomass since the rise of humans. So we see these very large changes going on. We can also see changes in the amount of carbon in the atmosphere, and that's depicted on this slide, which in the top part goes back to 3.5 million years ago, this right in the middle of the Pliocene. And on the left-hand scale is the carbon dioxide in the atmosphere, derived mostly from things like, well, there are various different ways of measuring the carbon dioxide in the atmosphere. We don't actually have any ice that's that old, but there are various other ways we can measure past carbon dioxide levels. And the levels at the time got up to 450 parts per million, or maybe 470 parts per million. And over time, that declined as we went into the Ice Age, which the Pleistocene, which started about 2.6 million years ago, and then declined further until it got down to a level. So for the past sort of 800,000 years, the maximum amount of carbon dioxide in the atmosphere, as represented in bubbles in ice cores, was about 280 parts per million, and the minimum was about 180 parts per million, which is very different from what it was in Pliocene time. And it's broadly thought that it's the decline in carbon dioxide through time that got us into the Ice Age in the first place. So we can look at that in another way. On this graph here, we're looking at the changing carbon cycle. This is carbon dioxide and methane compared with projections into the future. So down at the bottom, you're looking at the past 450,000 years or so. This is based on the Vostok ice core from Antarctica. And the red line shows you the way that methane has gone up and down. Now, at the present on the right-hand side, you can see a rise in methane and carbon dioxide. That rise goes into the Holocene. And then you can see these 1, 2, 3, 4 previous rises. Those are the past interglacials, the brief warm periods between successive glacial maxima. So glacial maxima around 360,000 years ago, glacial maxima around about 280, another glacial maxima around about 170, and the most recent glacial maxima over here around about well, it shows 50,000, but that's probably closer to 20,000 years ago. So you can see the way that with those changes in temperature, the carbon dioxide fluctuated. That's the blue line. And as we saw in the previous graph, the maxima were about 280 parts per million and the minima were about 180. Methane showed a very similar pattern. You can see the methane following the carbon dioxide, but the methane amounts are very much less. On the left-hand scale, you see it says ppbv, that's parts per billion by volume. So the methane concentration is about 1,000 times less than carbon dioxide in the atmosphere. And you can see 400,000 years ago, it was up at about 700 parts per billion. Where was it in 2019? It was up here where the red arrow shows at almost 1,900. So a very substantial increase in methane. And on the right-hand scale, you can see the carbon dioxide in blue got up to about 280, whereas now in 2021, it was 415. So what we're interested in is where is it going to go in the future? And we can see that during the past, the carbon dioxide level has risen. And we get to the sort of inflection point represented by the red dot. So the question is, where's it going to go next? We have some degree of control on that if we can master the way in which we're putting carbon dioxide and methane into the atmosphere. Will we make the concentrations decline? Will they decline steeply? Will they decline shallowly? Will they just sort of flatten out? These are important questions for politicians and scientists today. So let's look at the modern warming. So this is when I say the modern warming over the past 25,000 years. So you can see the red line shows the global cooling and change in temperature down to the maximum cooling around about 17,000 years ago. And then you can see the way the temperature rose towards the Holocene. This was driven by the changes in the Earth's orbit and the tilt of the Earth's axis. These large extraterrestrial astronomical variables caused our climate to change in this way. And carbon dioxide changed along with the temperature at the time. But for most of the Holocene, which began around 10,000 years ago, this has been rather, the temperatures were rather constant throughout the Holocene. And if we look at the small inset diagram, that shows you that right-hand bit blown up for the past 1,000 years. You can see that temperatures were in the late Holocene were more or less constant, a slight decline about 200 years ago, and then this really steep rise. And that's that same steep rise you see in the top diagram. So the modern warming that we see right at the end of these two graphs is the fastest warming at any time in the past 24,000 years, as represented by studies of ice cores. So that's a very rapid change. This is now blown up to show you the past 2,000 years of history. So on the left-hand diagram, you can see we're going from the year 1 right up to 2020. You can see the way that the temperature has stayed sort of more or less flat and then declined somewhat. And then since about 1850 or 1900, it really has shot up. These are the observed temperatures. And this warming that we see on the right-hand side there is unprecedented in the past 2,000 years. Now, what interested the climate scientists was to what degree is that climate natural, or to what degree would it be man-made? So on the right-hand graph over here, we're going from 1850 to 2020, and you see that the temperature changes, deviations from the average, are marked as 0.51, 1.5, and so on the left-hand temperature scale. And so thinking about what we know about the sun's behavior and about the way that volcanoes will have disturbed the atmosphere and when those volcanoes occur, we can demonstrate that the climate should have been now about the same as it was back in 1850. That blue line that goes across the middle of the diagram shows you that our climate actually should have shown very little change at all. However, what we find is that from about 1900 onwards, we start to get this temperature increase, and the observed is the black line and the model climate is the reddish line. So both the simulated and the naturally observed climate change deviated from what we would expect from the natural changes represented by solar and volcanic changes. That's the clue that tells us that it's something we're doing to the climate. Now, a lot of people ask me when I'm giving this lecture, you know, surely, Colin, it has to be the sun. So let's look at the solar influence. And what we're looking at here is total solar irradiance as measured by various instruments. And what we see is we're going from 1975 right up to 2021. And we can see the way that the total solar irradiance has zigzagged up and down following what's called the 11-year sunspot cycle. And there's another independent way of measuring that, and that is to look through a telescope and actually measure the sunspots on the surface of the sun, which is shown in the lower diagram. And you can see it's exactly the same. It shows these ups and downs. And the blue lines in both cases show that the sun's energy has been in decline. It's in a declining phase. So what's going on? Well, we know that the temperature has been increasing over this period. And so we can't blame the increase in temperature on the sun, because what we can see here is the sun's energy has been decreasing. We've got more data on the sun, for example, here. This comes from a astrophysics paper in 2014. What it shows is the sunspot cycle from about 1750. And so you can see as the 11-year sunspot cycle zigzagging up and down across the diagram. But what you can see is that it's modulated modulated by an underlying cycle so that we get periods of less sunspots, periods of more sunspots, periods of less, periods of more, and we're going into a period of less. This is due to two larger cycles than the 11-year sunspot cycle. One is called the Seuss-de Vries cycle, it's 208 years long, and the other is called the Gleisberg cycle, which is 88 years long. And those two work together to modulate the 11-year sunspot cycle. So if we were to go back to 1800 or up to 1820, we would have found the temperatures were very, very cool indeed. And that was because this was one of these periods of minimal sunspot numbers. And if we were to go back to the 1880s and 1900s, up to about 1910, we would see once again, we were in a period of minimal sunspots. And so the temperatures would have been relatively cool compared to today. So the question is, what was 1980 and 1990 like in comparison with these previous peaks in the 1860s and the 1780s? And what we find, and you can see the blue line I've drawn across there, is that we should expect in 1980 and 1990 that the temperatures on Earth should have been about the same as they were in 1860 to 1870, and about the same as they were in 1780 to 1790, because those were the peaks of sunspot activity. So we should be cooling. As you can see, from 1990 onwards, we should have been cooling. We're clearly not cooling, so we can't blame the sun. So we turn to something else, and that is greenhouse gases. And here on the right-hand side, you see this is the hand of a member of the British Antarctic Survey holding a slice taken off the end of an ice core. And when you look at this with the light shining through it, you can see all these little nodules. Those are bubbles of trapped air, fossil air. And the way it works is as follows. We have snow falling on the ground, and the snow falls very slowly, and it traps pockets of air, small pockets of air. And as more and more snow falls, those pockets become compressed as the snow's compressed, and eventually the snow is compressed deeper down into ice. And when it is, those little pockets of air are compressed into bubbles. So we have fossil air, and we can analyze that fossil air in ice cores, as you see in the diagram on the left-hand side. So we're going back from the year 2000 back to AD 1000. Up the left-hand side, you see the carbon dioxide scale from 260 parts per million to 400. And what all these colors between AD 1000 and 1769 show that all those colors and symbols represent different ice cores in Antarctica. And they all show the same thing, that we had about 280 parts per million in the air. So this represents the typical interglacial amount of carbon dioxide that we should expect in the air, as we saw from the previous graphs, which showed us going back 450,000 years in time. So a typical interglacial interglacial period, like the one, the Holocene we're living in, that's what its characteristics should be, and indeed that's what they are. Now, some of you might know what happened in 1769. This is when James Watt patented his steam engine, and everybody wanted one, and what they burned was coal. And so we see the carbon dioxide, as more and more people had steam engines, the carbon dioxide started to grow. We burned more and more coal, and we saw this big rise in carbon dioxide globally, and a very much steeper rise as time went by. So at the time I made this slide, already on the right-hand side, it was up at 410, so it had gone off the left-hand scale. Actually, it's now at 415. So what we are doing is we are increasing carbon dioxide in the atmosphere at about 20 parts per million per decade. And the fastest it happened in glacial times, according to all of our work on ice cores, is 20 parts per million in 1,000 years. So we're doing this 100 times faster than nature. And it's that increased amount of greenhouse gas that's helping to warm the planet. Okay, so you can see something else, another chemical signature here. We're looking at carbon dioxide again on the left-hand scale, the same data going from 1,000 right up to the year 2000. The black squares along the bottom show you those carbon dioxide amounts, showing very little change throughout that whole period. And then after about 1769, you see the carbon dioxide increasing in that black line. But what you see at the same time is the orange stuff. So look at the orange data going across here. That's the carbon isotopic ratio between carbon 12 and carbon 13. Right when we get to 1769, you see that suddenly starts to change. So you see the carbon signature dropping off. Now, what this is telling us is that the signal, the isotopic signal we're now getting in our carbon dioxide that's being emitted throughout this whole period is typical of fossil fuel. So the more fossil fuel you burn, the larger the carbon 13 signal becomes. So we know where this stuff comes from, basically. And a lot of it's being emitted by the US. In the US per capita, they're emitting 16.5 tons of CO2 per capita. In China, just 7.6 tons per capita. But we have to remember something about China, and that is that the US and Western Europe, including us, decided in 1980 we were going to, with deregulation, we were going to export our businesses to where the work could be done cheaply. So a third of that Chinese emissions is actually done for the businesses that we exported to China. So it's done for us. India, 1.6 tons per capita. And that's more than most developing nations. So when did we start perturbing the carbon cycle? Well, we can go on this graph back to 1850, and you can see very little coal being burnt at the time. This is millions of metric tons of carbon being produced into the atmosphere. You can see that coal use grew slowly, represented by the orange. And then after 1950, you can see it started to climb fairly significantly and quite steeply towards the end. Oil, we were burning little bits of oil back in around about 1910, small amounts. And you can see that gradually increasing. Then after 1950, really whacks up. Huge amounts of oil have been built in 1950. Small amounts of the bluish gray natural gas being burnt back here, back into the 1920s, and then a very significant increase after 1950. The one that may surprise you here is cement. That's simply because cement is made from using calcium oxide, and calcium oxide we obtain by heating limestone, which is calcium carbonate, and the carbon dioxide is given off and goes into the atmosphere. So it's a small additional contribution. Now the orange line is 1950. And what we know from this diagram is that more than 90% of all the fossil fuel ever burned has been burned since 1950. Now I was a kid in 1950. So all of this has happened, as it were, on my watch. So it's very recent. So everything that went before is my grandmother's era, or your grandmother's era, or your great-grandmother's era. And the world we live in now is vastly different from grandma's time. So let's look at some of the indicators that are indicators of anthropogenic change. So on the right-hand side, we've got these three little graphs. The middle one with the dark black line shows you the increase in temperature. The bottom line, the scale bar goes from 1700 right up to about 2010. And you can see the way in which there's an almost exponential increase in in temperature with time, which follows the that exponential increase that we just looked at in carbon dioxide. Now, when you warm the earth, you're warming the ocean as well. And when you warm water, the thing about it is the water expands. So you expect the sea level to go up. Equally, when you warm ice on land, it melts and the meltwater goes into the ocean. So the net result of all this warming is that the sea level goes up. So you see not much change between 1750 and about 1850, maybe a slight increase. But then you can see how we're starting to see this significant increase in sea level with time due to all this warming. We'll talk about sea level more later on. Up at the top of the right-hand graph, you're looking at nitrate. Now, the reason for looking at nitrate is because it's used as a fertilizer. So we see for most of this period, 1700 right up to almost 1900, not much change in the amount of nitrate being used as a fertilizer. And then we start to see from about just around about 1950, we see this big increase in nitrate. And that's measured in Greenland ice cores, and it reflects the huge amount of increase in nitrate fertilizer which began around about 1910, but then ramped up significantly after 1950. Now, from the orange curve, what you see is that the nitrogen isotopes in the nitrate fertilizer showed very little change up until about the mid to late 1800s, and then that started to decline just when the nitrates started to grow. And then from about 1950, you see a really steep drop off in the nitrate signature. So this is all indicating that we are now relying predominantly on artificial fertilizers. So we've got increasing nitrate with a very different nice isotopic signature. When we turn to the left-hand side, I'll start with the bottom diagram first. We're going from 19, that's 40, 50, 60, so that's 1930 on the left. This is DDT. And so what you're seeing is very little change in DDT or these other compound, toxaphene, which is a similar sort of compound, right up to about 1950. And then you see how the DDT signal starts to rise. You can see how the DDT in the blue starts to rise. And then it drops off somewhat because we tended to stop using it in Western countries, but still carried on using it in developing countries. And the other one compound used in nature is toxaphene. You can see how that also rose after 1950 and is still abundant. So we have these chemical signatures that we can see in sediments and other materials because these are very long-lasting organic chemical compounds. And in the top diagram, which is slightly complex but really simple, it's the radionuclides from 1945 right up to the present. So 1945, we had the first A-bomb test that put a little bit of plutonium into the atmosphere. So we start to see a tiny plutonium signal then, but it wasn't until about 1953 where the first H-bomb test, you can see the wave from 1950, the plutonium signal just starts to ramp up and then it gets massive right around here in 1955, lots of bomb tests, and then further bomb tests in air around about the late 60s before the test ban treaties came into effect. And in the background in orange, so we can see plutonium all around the world as a long-lived signature of change, which shows a big signal starting in about 1950. The orange in the background is the ratio of these radioactive iodine compounds, which we are measuring in corals. And again, you can see how after 1950, how this really ramps up. So we now have big iodine signatures. So we can follow these around. We've not only perturbed the nitrogen signal, nitrate cycle, also the phosphate cycles. So here you see up until about 1950, just very slight change and slight growth in the amount of phosphorus production. And then you see how that really starts to ramp up from about 1950 or just before onwards, and blue in the United States and then gray for the rest of the world's total. Now, the phosphorus and nitrogen cycle is important in two ways. First of all, we do use it for fertilizer. We put it on fields, but usually farmers laid tons of this stuff on the surface. It doesn't all get down into the soil. As soon as it rains, a lot of it washes off. It gets into the rivers and it just flows downstream. And when it comes out into the ocean, it stimulates the growth of algae, and the algae eat all the oxygen in the water, and that kills off all the fish life. So we have these big biodiversity changes in places like the Baltic and the Gulf of Mexico around the Mississippi Delta. Here's another thing that we've changed dramatically too, and that is represented by these diagrams showing the growth of dams in the United States. So very few in 1850, mind you, there was almost nobody living west of the Mississippi at the time. We can see that by 1900, we've still got more down the East Coast, but look at 1950. By the time we get to 1950, virtually the whole country is fairly densely covered with dams. The white areas represent the Rocky Mountains and the southwestern deserts. By the year 2000, it's even more dense. And dams are important because dams block the supply of sediment to the river mouths. We'll talk more about that in a moment. By warming the planet, we've also changed the ice profile. So here we're looking on the right at the Arctic and on the left at Antarctica. So at the top circular diagram, you see the Arctic Ocean is an ocean surrounded by land, and the white arrows show you that warm air can get in from almost anywhere. And the red arrows show you warm ocean water can get in from the Atlantic. And what that does is it helps to melt the sea ice. So in the diagram below that, you see from 1978 to right up to 2020. Why 1978? That's because that's when satellites began measuring Arctic sea ice. And so what you see, this is for January. So this is winter sea ice. You can see how the winter sea ice has gradually declined with time. So we've lost a very significant percentage of sea ice, even in the middle of winter. And if I showed you the summer one, it would be a vastly steeper decline with a serious loss of sea ice. When we go to Antarctica, we see from the bottom graph, things are very different. This is January in Antarctica, which is the middle of summer. And we see since 1978, there's a lot of hopping around above and below the zero line, showing some years when we gained ice, some years when we lost ice. And the most significant change has actually been in 2016, 17, 18, 19, when the ice loss was much more dramatic than it had been in previous years. And nobody is quite sure why, and we're not sure whether that's going to continue, but it's a signal that is alerting us to the need to keep monitoring this stuff. Now, the reason that we see very little change around Antarctica is because it's a continent surrounded by oceans, very different, the exact opposite of the Arctic. So around Antarctica, we have very strong westerly winds running, and they force the Antarctic circumpolar current, which is a massive current running around the continent. And those two together, the wind and the ocean current, together act like a wall that helps to keep warm air and warm water from the north from getting into Antarctica. So we see very little sign of warming in Antarctica, except over here in the Antarctic Peninsula, which is close to South America, and that's because that's sticking up well north of the Antarctic Circle. So it's a much warmer environment than the rest of the continent. So sea level rise and deltas. I was talking about the fact that with all those that change in the hydrological cycle, we've stopped sediment getting to the deltas, and what that means is that the deltas are now sinking under their own weight. So this is just a collection of large deltas, the Chao Phraya over in Thailand area, then Mississippi, the Ganges, the Yangtze, Mekong, several big rivers, all losing, and the Nile would be the same. They're sinking into the sea under their own weight. All the accumulated sediments that were accumulating there, these deltas are now sinking. And that's independent of the effect of sea level rise. This is their actual physical sinking. And so, in a sense, the delta areas are getting a double whammy because they're sinking under their own weight because you stop sediment getting to them, and we're also causing the sea level to go up. We're changing things in other ways too. This picture of the globe on the right shows you for all these brown areas, this is where through our intensive agriculture, we've almost fully transformed the soils by deep plowing, and we're beginning to make those soils carbon poor and less nutritious than they were before. So we're having a serious effect on our soils, which ultimately, if we're not very careful, will have a serious impact on our agriculture. On the left-hand side, what we see is what's going on in typical tropical regions. This is in Sumatra, and it shows you a river running across what used to be a tropical forest. All that tropical forest has disappeared, and it's been replaced by palm oil plantations. All these little black dots you see in the foreground, each one of those is a palm oil plant. So this is a very much less diverse environment. It's got hugely less biodiversity, and it's also much less capable of absorbing carbon dioxide from the atmosphere in the way in which a tropical rainforest would have done. So one thing we're looking for in sort of mapping out the Anthropocene vertically down sections and cliffs and what have you is new materials. So here what we're looking at is two things. On the left in red is the production of aluminium in millions of tons. And as we see from the red dots, almost none, right up to about 1950. Then you see the aluminium production really begins right about 1950, and then it really takes off considerably right up to, on the left-hand scale, 500 million tons per year. The blue is our production of concrete. Again, you do not much change right up to about 1950. It really starts to take off. You get this exponential increase, and that gets up also to 500. But in this case, it's a different 500. This is billion tons of concrete. So we are producing annually 35 million tons per year of aluminium and 27 gigatons per year of concrete. So the annual concrete production, as it says down here, is around about 27.3 billion tons per year. And that is the same amount as the total flux annually of all sediments from rivers, all aeolian dust blowing off into the ocean, all ice sheets contributing sediment to the ocean, all glaciers and coastal erosion. So this is why we say humans have become a geological force. There's this much aluminium has been produced as pure metal to be able to create enough aluminium foil to completely cover the United States. And here we see on the right typical modern city, glass and concrete. And it turns out the past 20 years of construction accounts for half the concrete ever produced. That's just in the past 20 years. So the total we have there would spread out to about 1 kilogram per square meter across the planet. So it's a ridiculously large amount. Now, ever since we started burning coal, we also produced novel lithostratigraphic indicators, and here is one. These are carbonaceous particles. That's scale there is 20 microns, so they're tiny little things. Looks like a piece of pumice with button holes in it. And they come out from factory chimneys, mine chimneys where fly ash is being allowed to escape into the environment. So let's look at the graph that goes back to about 1830, and the different colors in the inset box there show you the different areas where this stuff's been produced. And so we see that its production from burning coal increased gradually, just like our use of coal, and it really steepened around about 1950. You see that massive steepening. This is just another one of the steepenings we've seen, like with aluminium, like with concrete. Here we're looking at fly ash, and this is labeled, this point is labeled the great acceleration because it's a great acceleration in a great many things. But what we see here is that this tailors off. You can see these peaks start tapering off after about 1975, and they're beginning to go quite down. And that's because around the world, governments have agreed that we need to stop pumping out fumes from coal plants into the air because it's damaging for human health. Underneath the graph of the colored lines is a gray shading, which represents soot, or what's properly technically called global black carbon, that also increased with the burning of coal between, after the 1870s, as you see, and also increased fairly steeply after 1950. But that too has begun to peak and drop off. And soot is rather important because it is one of those aerosols that's not reflective. Many aerosols, that's dust particles we put into the atmosphere, are actually reflective. They can reflect the sun's energy, and that would tend to cool the climate. But soot, which is black carbon, absorbs solar energy, and so it tends to warm the atmosphere. So when we're trying to calculate global warming, we have to bear in mind not just the greenhouse gases, but also the aerosols. What other novel mineral and chemical indicators do we have? Well, loads, as it turns out. If you go back to 1700, a little windmill picture on the left, excuse me, the main sort of elements we would be using then would be carbon, calcium, iron. But by the time we get to the year 2000, after going through James Watt's steam engines and then the rise of the motor car and so on, We're now in the area of catalytic converters in car engines, of offshore wind plants, of solar arrays. We've all got computers, we've all got mobile phones. All of these require huge amounts of chemical substances. So it turns out over this time, we humans have produced 180,000 synthetic mineral-like substances, like the ones in your mobile phone, whereas nature in 4.5 billion years has produced only 5,000 mineral-like substances. Also, during the same period, we've produced more than 85,000 industrial organic chemicals, like the DDT that we talked about earlier. Some of these chemicals, we can see signals dating back quite some time. This is a core through a Spanish lake. It's on the edge of the Mediterranean. And so not surprisingly, 3,000 years ago, we see this big peak here for the production of lead by the Greeks and the Phoenicians. And then their influence died away and it was replaced by the Romans in the around about 2,000 years ago. And so there's a peak there, and then Roman influence declined. And then what we see is in very recent years, we have the huge Anthropocene peak from lead in petrol. So that's a modern indicator. Here's another one, plastic. We all know a lot about plastic these days and how we need to stop putting it in the ocean. Going back to 1950, in 1950, all that we produced was 1.7 million tons in a year. Now, we're producing 299, say 300 million tons per year. And if you add that all together, we produced enough plastic to convert it into kitchen wrap, plastic kitchen wrap, and we could literally wrap the whole of the planet in that. And here we see an example of some geology. This is an old piece of plastic stuck in beach rock. It's actually a Spanish beach rock. So plastics are now forming part of stratigraphy. Now, the kinds of products that we produce, including plastic products, are actually useful in the Anthropocene context because they change through time quite rapidly. You know, each year some person manufacturing toothbrushes wants to produce a different variety of toothbrush. We know when they were produced. If we find them in sediments, we can date them pretty accurately. And the same goes for knives and forks and spoons, cutlery, toothbrushes, ballpoint pens. Look at the way the phones changed. These large brick type phones were the ones I was familiar with in the early 1980s. Now we get down to these little ones, and now they're actually getting bigger with the iPhone. Plastics have changed through time. The kinds of books and CDs and tapes we use have changed. Clothing, even the humble clothes peg and the humble paperclip have changed. So has the humble nut and bolt. So when we find these in the geological record, they will help to date it. We've also perturbed biodiversity considerably. So these are just a few examples of where, for example, in New Zealand, the number of native species is almost 1,800, but the number of invasive species, most of which were taken to New Zealand by Brits, is now about 1,600. Hawaii has had similar introductions of people and their plants. So you can see almost as many invasive species in Hawaii as there are natives. Let's go to Tristan da Cunha. It's the other way around. There are more invasives in Tristan than there are natives. Let's go to South Georgia. Again, more introductions than there are natives, and so on. You get the picture of plants, fish, whatever, you can see them. I'm reminded, it's not on here, but I'm reminded that one of the reasons you find starlings and sparrows in places like New York is because back in the 1800s, a Brit going to New York decided that America needed the same birds that were mentioned in Shakespeare. And so he took them there. Right, so there's a big challenge though with biodiversity and climate change, because if we look at on the left-hand side, we're looking at a Canadian boreal forest in good health. On the right, we're looking at a Canadian boreal forest in extremely bad health. And the reason is with the warming, the pine bark beetle is now able to have 3 reproduction cycles in 1 year, whereas previously it had 2. and the birch had evolved to keep pace with 2 broods of pine bark beetles, but it couldn't keep pace with 3. So you can see all the bark has been taken off these trees. And that means these forests are dying from insect infestations. So let's just think about the way we've changed things. Along the bottom, we're going from 1900 up to 2020. And here we see from 1900 right up to about 1950, not a great rate of change. This is when our populations were, down less than 7 billion. But by the time we, in fact, by the time we get to 1950, population was, human population was 2.5 billion. Now the population is 7.5, and with that growth from 2.5 back here in 1950 to 7.5, all of these things have grown tremendously. Metals production, asphalt, bricks, aggregates, concrete, plastics, all of them grown fantastically. And so again, this is a message not only from fossil fuels, but also from our productions of stuff that we've seen this. There's a major disconnect right here at about 1950. You can see that also in this graph. What we're looking at here is the change in energy use. So at the top is the global population change rising from 1950. And here we see how the global energy changed from 1950 onwards, and so did global productivity. So what was going on here? Well, it turns out the 1950 is important. It's what you might call a singularity. It's a massive sudden change. Everything after it is different from what went before. And the reason is during the Second World War, industry globally adapted to producing, particularly in the United States, warships, tanks, bullets, bombs, fighter planes, and all of the other accoutrements of war. With the production lines, they were tremendously efficient. And so we had this massive flow of stuff coming for the military. However, when the war stopped, we didn't need all those guns and bombs and tanks and submarines and bullets and, Spitfires and whatever. And so industry had to think about what it was going to do, how it was going to survive, how it was going to grow. And Madison Avenue joined the plan, and we all became persuaded to buy stuff. So wartime production changed to produce stuff, and we bought into that, and so things have been going up ever since. And the rate of change in this short period has been very much faster than the rate of change at the Paleocene, Eocene thermal maximum, which was the last time we saw a massive change in carbon dioxide. So what's happened to sea level? Okay, well, this is satellite data from 2003. And we believe it's entirely valid because for early periods going back to about 1750, this line connects with all of the tide gauge data from around the world. So we can see that sea level's been going up. And I put my ruler through these 4 collections of consecutive satellite data. And you see the ruler line carries on going straight, but the satellite data show that the rate of sea level rise has been increasing on a sort of exponential pathway, which is kind of what you'd expect from the way that the temperature is increasing. So there's a message for us that if we continue warming, we are going to see an increasing rise in sea level. Now we can take the long view of sea level, and it's very informative. So what we're looking at here, this is a paper from Clark in 2016. So what we see here is we're going back 20,000 years in the time scale. And so 20,000 years is the last glacial maximum. So we have these low sea levels, probably minus 130 meters compared with today. Then we start to get that warming that we looked at earlier in the temperature graphs. And as the world warms, so sea level rises because we're melting ice and we're heating the ocean. But the orbital forcing that drove temperature and carbon dioxide changes, that stopped round about 12,000 years ago at the beginning of Holocene time. But the sea level went on rising. So what's going on? Well, it turns out there is a lag in the system. it takes a long time for sea level to catch up with the warming that we had earlier. The climate optimum in the southern hemisphere was reached about 9,000 years ago, and yet the sea level just carried on rising by 45 meters from about 12,000 years ago, the beginning of the Holocene, up to when it flattened out and there was almost no more ice melt. I mean, this is really extraordinary, but it tells us something about our future. Right now, we've warmed up to here and our sea level has gone up. Now we're trying to stop our warming, but the sea level is likely to go on rising because the amount of heat that stays in the atmosphere is still going to go on melting ice. Even if we stop adding carbon dioxide to the atmosphere, it's still going to be there. And so we must prepare for a very significant temperature rise in the future. And here's an example of what happened in the past. I'll go over this quite quickly. We're looking at the Eemian, which is the last warm interglacial, around about 127,000 years ago. This is when the warmth was most extreme. And what we see here is the sea level rise curve determined from data from the Red Sea. And so 130,000 years ago, sea level was lower than the present, which is 0. And then it rose right up to this level, which is plus 15 meters. And then gradually it began to fall, and it showed these sort of slight ups and downs. Now we can decompose that signature, that global signature, into two, into the Antarctic contribution, which is in green, and the Greenland contribution, which is in blue. So you see that the warming first affected Antarctica most, and then gradually Greenland got into the act as well. So we can expect to see Greenland and Antarctica behaving in similar ways in the future. But we can also expect that if we're stupid enough to carry on warming the world the way we are, we can expect sea levels to be as high or even higher than they were 127,000 years ago in the last warm interglacial. Right, so let's talk about how we define the stratigraphic Anthropocene. I've shown you, for example, I've shown you data, so heavy metals, organic compounds, fly ash, black carbon, the carbon nitrogen signature, microplastics, and so on. We've got ecological indicators from pollen diatoms and all these other things. We can see human modifications from sedimentation, from erosion, from mine tailings, from refuse and landfill, our buildings and infrastructure, urbanization, agriculture, and so on. We can see oxygen isotope and other signatures, nitrate, carbon dioxide, and so on, radionuclides over here. We've got radiometric dating, and then of course we've got annual laminae and varves and so on to date things. So this is where we're looking at the moment. We've got these various places: San Francisco Bay, a lake in California, a lake in Canada, corals in the Gulf of Mexico. We've got an ice core from Antarctica, more corals from the Great Barrier Reef. We've got coastal sediments from Japan, another lake in China. We've got the Baltic Sea itself. We've got peats in Germany. We've got caves, speleothems, and we've got urban soil in Vienna. So let's look at some of those. This is the Searsville Reservoir in California. Dam was built in 1891, so we have lots of sediment buildup, and you get these lovely layers in the sediment that you can see going on here. Annually resolvable chronology, so we can see changes. We can figure out where 1950 is, and we can see the changes there. In the Antarctic Peninsula, we've got a nice core from the British Antarctic Survey that goes back to the beginning of the Holocene, 12,000 years or so. And these are methane in orange and carbon dioxide in blue. And you can see the way those have changed dramatically in recent years. So we've got enough ice core at the top end to be able to see what happened as we go back to 1950 and before. Crawford Lake, Canada. Here's the lake over here on the left. And we've got these beautiful annual varves formed in this lake. A nice record of industrial markers. Here we are in the Baltic Sea, in the East Gotland Basin. up near Sweden, and we've got these beautiful bedded marine silt and clay successions down in about 250 meters of water, multi-proxy sediment chronology, and distinct radionuclide signatures, and so on. And here we are. This is a section through a stalagmite. What we can see is this little yellow line. You might not be able to see that yellow line there is the 1950 line, and this yellow line here is the 1975 line. So we can analyze the chemistry before, during, and after in order to see what the changes are, to determine where the best place is to place the Anthropocene, the base of the Anthropocene. And here we're on the Flinders Reef off Australia, looking at corals again. You can see these beautiful coral growth rings. Again, we have a chronology there that goes from 2017 right back to 1700, and it will show us all these things like seawater temperatures, radiometric changes, and so on. And I think this is the final one. West Earth is the reef on the shelf of the Gulf of Mexico. The core goes from 1753 to 2005, beautiful core, lots of laminations, and so we can get all sorts of water chemistry records and also industrial records from that core. So just to conclude then, it's obvious to those of us working on this that, that Paul Crutzen was right. There has been a massive dislocation at the end of the Holocene into something that is now completely different, which we are proposing should be called the Anthropocene. And we can already see the units, the geological units. They're thin, they're young, they're discontinuous, but they're also globally distributed. They have got these distinctive chemical, physical, and biological signals in them. Those signals are larger than the Holocene for carbon dioxide and methane and carbon-13, or the signals are entirely novel, like aluminium, plutonium, concrete, plastic, fly ash, and so on. So we can characterize these sediments as very different from Holocene sediments. And the changes that we're seeing are either long-lived or irreversible. And I showed you the sea level example. You know, the sea level, just as it did at the beginning of the Holocene, when warming flattened out and we got this sort of long warm period, the sea level just went up rising by another 45 meters. Now, it's not going to rise by 45 meters in our future, but it may well rise by the 15 meters that you saw from the Red Sea example. And these trends are continuing. So the warming is continuing, the sea levels are continuing. We're still getting more and more invasive species as people transport organisms around, and we're getting a lot of biological extinctions. So the biota is changing as well. Now, some of these signals have yet to breach the Holocene conditions. Already the temperature has just gone beyond the Holocene maximum, but the sea level hasn't yet got there because it's got this built-in lag. But it is moving in that direction. So we have to recognize the effects of lags in the system. So what do we do now? We submit our candidates for these global stratotype sections and points to our parent body, which is Subcommission on Quaternary Stratigraphy. And if they like it, then they will submit it to the International Commission on Stratigraphy, which is the body that decides whether or not the case is made for a new geological boundary and timescale. And if they do, they will then have to present it for ratification to the International Union of Geological Sciences. So there we are, that's the end. And if you do have any questions, I'd be very happy to take them.